There we go. Thank you. Thank you.
All right, I'm Harry Quackenboss. There's a collage of some cars I've worked on, most of them pretty old. I got involved in a project with some GM engineers who were moonlighting an apprentice for a while and ended up getting involved in suspension specialties. Picture in the middle is an IMSA Corvette that I worked on with a guy named Jerry
Harry, your screen, I don't think your screen is sharing right now.
Ah, okay. Indeed not.
Sorry about that.
No worries.
All right, I think we're good to go.
Very good. So as I was saying, a collage of pictures, the Corvette in the middle there, I worked on with a guy named Don Yanko, who was sort of famous for a variety of exploits, owned a Chevrolet dealership. Somebody found that on the web a couple of weeks ago and sent me a picture of me hovering over the engine with one of the other engineers. I also worked on a car that's not all that different from a Formula SAE car at the top. Some of you may be old enough to remember Malibu Grand Prix. This was the predecessor project, which was powered by a snowmobile engine. And also spent a lot of time autocrossing a Corvette on the right there. So in my experience in working with the Formula team, I have some observations that I've kind of tried to summarize here. Unfortunately, this isn't very brief, but the first point, which you can read, and I'm going to make the slides available to you. First point is that simulations are great, and they've clearly gotten better. But in the end of the journey to building a car, what counts is how you do on the track. And so if the track results are different from simulation, which they pretty much almost always are, then the challenge is to figure out how to make the simulation better. That's one observation. Another is, because of the various complexities around vehicles and the combination of things going on, it's pretty easy to zero in on some aspect of the car, spend a lot of time and money that has less impact than some other area, or vice versa, to ignore things that might be pretty important. And so I think one of the lessons is to try to keep the big picture in mind. Next point is the math is definitely important, but if you can relate the math to some simple description of what's going on from both the car and the driver's point of view, you'll be better off. And finally, if what you think is different from what the top teams in similar cars are doing, then more often than not 100% of the time, more often than not, they'll be correct and your analysis and assumptions are probably wrong. And the final point is a quote from Albert Einstein that I'm not actually sure he ever actually said. But his point is, simplicity in general wins, but there's a fine line between simplicity and going too far. So as an example, to give you a perspective on that, here's a car that several of people on the team have looked at. I read about this a couple of years ago and pointed it out to people. So this is an autocross vehicle. It's powered by a turbocharged 1000cc Yamaha snowmobile engine with a CVT transmission. If you don't know what a CVT transmission is, it's a variable belt drive. If you've ever driven a snowmobile or a variety of low-end scooters, they use them, where you have a belt drive and a pulley that can change diameter based upon how fast it's spinning. And so it's kind of an automatic transmission, but they call them continuously variable, or CVT for short. This one also uses a suspension design you can see in the picture, which is a type of independent suspension that's linked together called a Dion. And the particular linkage arrangement with if you look at the picture up close, you can see lower control arms that attach to an outside structure. There's a black tube horizontally across the back of the vehicle, and the links are angled in toward the center of the car. And then you can see the upper links are parallel. I think I can probably point those out with the mast. So that's the upper link, and then the lower control arm link attaches there and runs forward to attach this frame structure of the car. So a few things are obviously different about this from a Formula SAE car. One, you can tell the rules have much more liberal dimensional constraints on how big the wings can be. And so this is actually a pretty long car with a fair amount of overhang. But this car does almost 3 Gs lateral. It'll generate 1.4 Gs under acceleration and about 3 Gs under braking. And that was a great quote in the interview with the car builder. It says, what was the favorite change? And they said, the one we got it to stop trying to kill us when we drive it. But this thing's probably got, I'm guessing, 300 horsepower, something like that. And probably weighs about what a Formula SAE car is. But it's a good example of a relatively simple car. If you look at it, it doesn't really have much of a body. It's got wings, but no real body. Here's some suggested resources for learning more. There's a ton of stuff already in the Google Drive. I think most of this is there, but again, I'll make the slides available. So I provided a riddle. Anybody get the riddle? Nobody's
90.
90? Yeah, exactly. All right, so let's think about this. So how fast is 60 miles per hour in miles per minute? It's 1, right? Divide an hour by 60. Everybody understands that. So if you go 30 miles per hour for a half mile, how long does that take?
1 minute.
Right. So if you've spent a minute to get to the top of the hill and you have to average 60 miles an hour the whole way, how much time is left to go the remaining half mile?
0.
Yeah.
Right.
Impossible.
Yeah, so you have to go infinitely fast down the backside. So the point of that is, when you think about time on a track, what's important is not what the average speed is. What's important is the lap time, typically in minutes and seconds, and your relationship to your other competitors. And so that actually has a pretty big impact. Has anybody heard of the accordion effect that happens on a racetrack?
Yes.
So basically cars get bunched up coming into a corner and they spread out going down the straightaway. And so if you think about the difference between a car in front and a car following in terms of seconds for the same amount of time at very high speed, the distance between the two vehicles is going to be much greater than it is at very low speed. And so you talk to a rookie driver and they say, well, I just kill them in the corners, but they have so much more power than I do coming out of the corner. Not usually. It's usually a function of the fact that the speeds are really different. If you're competing with other cars on a track, this phenomena is also pretty important to passing, because what it means is that if you're close enough to the car in front, what might translate to several car lengths down the straightaway can actually become an overlap between the two cars, where the difference in space for the same time at low speed is actually less than a car length. And that gives you a passing opportunity to get either on the inside or outside of somebody. Another point about sort of high-level observation, that there are a lot of different parameters to how you can adjust a car. And the theory might be that there's one optimal, but in practice, there can be multiple points on a complex multi-dimension surface where you can find local optima. Just as a hypothetical example, for one person might tune the car, the identical car, to be 0 camber, 13 pounds per square inch tire pressure, a spring rate of 350 pounds per inch, and somebody else might go exactly the same speed with negative camber, more tire pressure, and softer springs. And so the trick is to find a good combination that provides what I would describe as a local optimum among a combination of some independent, but also a bunch of interrelated variables. So we'll talk about some of those. The other point in terms of testing, in general, the way you approach getting a car is to go fast is the first thing you want to do is to get it to work at all. And then you work on reliability, and then you can work on tuning. And there's a variety of tools you can use, from a stopwatch, photoelectric cells, various telemetry things on the car, G-force, RPM, speed, wheel sensors, brake pressure, a whole bunch of things. And also there's a whole category of things you can do with respect to photos and videos, pictures of the car. And then finally, driver feedback is also crucially important. The best cars in general are easy to drive. And so getting driver feedback about that's really important. So this is sort of a complex picture, but I did a flow chart of all of the forces. And so let's sort of walk you through what's going on here. So from the car standpoint, the only thing that determines how much force you can put to the ground, which is what affects how fast you can accelerate and what direction the car is going and how fast you can brake, corner, and so on, is the tire contact patch. So everything that the car does gets transmitted through the tire. Very simple concept, and but it's important to keep that in mind. So the tire's obviously mounted on a wheel. It's attached to a hub assembly. It goes to an upright assemble called a spindle or a knuckle. It goes through ball joints, control arms, pivots, the frame brackets, and then there's the steering column, the steering gear, the steering tie rod ends that tie into the suspension, the frame, the seat attachment, the padding, and then the brake system, the calipers, the brake hydraulics, the brake pedal linkage, and so on. All of the things are sort of tied together. Every one of those areas is an opportunity, either where something can bend, it can break, it can have stiction or slop. And so all of those various points in the car can introduce nonlinear behavior. The other point is, I have two big red arrows on the chart. We'll talk a little bit about tires. Tires are what I would describe as nonlinear things. They're very complex to model. They're unpredictable. The chemistry changes. A lot of them, you heat them up and run the car, and the tire performance declines after some period of time. And the other thing that's nonlinear is the driver. The driver can be overconfident. They can be scared. They can be complacent about the behavior of the car. And so everything else in between those two extremes is kind of high school physics. It's fairly complex because they're a combination of things, but it's pretty straightforward in terms of how they look. But the two nonlinear points are the individual, the steering wheel, and the gas or the accelerator pedal and the brake pedal, who is putting inputs, the controls with those things, and the shifter. And the other nonlinear is at the other end of the system. And that's part of what makes this a complex process. So let's talk about tires. So first of all, they perform several functions. One is they hold up the car. They dampen out vibration. They're a source of transmitting force between the vehicle powertrain and the brake systems in acceleration and deceleration, and similarly transmitting force from the steering system in terms of cornering force. So one of the effects of tires that often is overlooked is that the spring rate of the tire is an important part of the overall suspension. Go-karts, for example, don't have conventional movable suspensions. So the tires comprise, along with some flex in the chassis, the spring rate. But one of the things to keep in mind with respect to, and these numbers are for Formula Car tires, the 18-inch Hoosiers that the team has been using up until recently, is that the spring force, the spring rate of the tire is actually a function of how much air pressure it's running. Now, with respect to this chart, the way to think about it, if the car with driver is 800 pounds and that translates to 200 pounds per tire with 4 tires, in general, the higher loads aren't really applicable to the range for a Formula SAE car. because this would go up to a 1,600-pound car. But with respect to what we're doing in the formula car range, 200 is probably on the high side, and air pressure is probably less than 14 psi typically. So a question at the bottom: why would you fill your tires with something other than air?
Because you don't have access to clean, dry air.
So yeah, exactly. So for example, nitrogen is pretty popular. I think for street cars, some of the dealers and tire shops will charge you extra to fill your tires with nitrogen, but its absorption of moisture is less, and so filling it with nitrogen is a way of assuring it doesn't have moisture in it. And if there's high moisture in the air, you're going to get higher pressure variation as a function of temperature, for example. Okay, a concept that I'm sure all of you are familiar with from high school physics is the concept of coefficient of friction. And so back in the 1960s, people observed a funny phenomena. The assumption was that tires conformed to a maximum coefficient of friction of 1. And if you do the algebra with Newton's laws of motion, a maximum of 1g coefficient of friction would say the maximum a car can accelerate if you're putting force through the tires as opposed to a jet engine, for example. If you're putting force through the tires, then obviously a maximum of 1g would mean that a quarter mile would be kind of the limit, equivalent of the sound barrier, and the quarter mile would be about 8.5 seconds with an ending speed of about 185 miles an hour. It's one minor point. If you look at drag racing times, the way they actually measure top speed is over a short distance prior to and after the finish line of the quarter mile. And so the trap speeds aren't really the same as the instantaneous speed at the end. It's an average over that period of time, and the cars are typically still accelerating. But in fact, the times broke 8.5 seconds in the 1960s, and so people went back and looked and said, well, there's a bunch of things going on we don't understand about the tire. And so they've done a bunch more analysis than that. And while the models are quite sophisticated with tires, they're still very hard to mathematically analyze the way you can, for example, a mechanical structure for stiffness. NHRA drag racing has actually stopped using the quarter mile because the speeds got so high. So they've shortened up the distance a bit. I think it's now 1,000 yards. But the last drag racing event that actually ran a quarter mile for competition, the ET was 4.4 seconds at 300 and some odd miles per hour. So obviously way higher than 1.0 in terms of the actual traction coefficient. So the reason is, and if you talk to Esther, she's got a whole presentation on this phenomena, but there are a bunch of what I would call non-Newtonian factors here. One is basically hot glue. So you look at the tire, it kind of melts. Another is that the track surfaces are not actually smooth. And so the tires dynamically deform to the irregularities in the surface. And again, there's some other factors here. Can anybody think of a non-tire factor that would account for that sort of top speed?
I don't understand the question.
Well, so what I was getting at is if you could increase the vertical load without increasing the mass of the vehicle, if you could push harder, then the force in the z-axis is actually higher than the force of gravity.
Oh, so you're just talking about Aero?
Yep. Or mechanical grip, right? There could be some mechanical factors that give you transient behavior there. If we have time, I'll show you some pictures. Okay, so the other important way that people talk about tires is what's the contact patch, and this just sort of illustrates that they deform in inconsistent ways as you increase load. So these things are hard to model. Temperature affects the adhesion, the spring rate varies, pressure varies, they're out of round, they wear, they degrade as you cycle them, you run them, the tires get hot, they eventually, the rubber chemistry starts to change and they lose traction. Some tires, it's pretty quick, maybe within a few laps. You can flat spot them, they degrade over time. And the spring rate actually changes because structurally the tires start to break down. So if you ever looked at a cutaway of a tire, it's a combination of various layers of steel and fabric and rubber. And so you can imagine that as the tire goes over bumps and it stretches and deforms over time as it gets squeezed, kind of the way squeezing a tennis ball is, internally the bonding between the rubber and the fabric starts to break down. And so the tire spring rate of a used tire is going to be different, typically softer than that of a new tire. Just to emphasize the point about asphalt, if you look at it closely, you can sort of see that pretty much any asphalt surface, it's got some sort of deformity, pebbles, little things that go on and so forth. Concrete's kind of unique. You often have expansion joints which can change the surface. In general, there aren't huge differences in traction between asphalt surfaces and concrete surfaces. And so, for example, at Lincoln, the back straight at Michigan, those are, I think, concrete. Crows is concrete, Park and Ride is asphalt. But the abrasive characteristics can actually be pretty different between the two. So you kind of summarize those things. In fact, hard packed clay can look a lot like asphalt. Again, all those things, the track surfaces, especially with rubber buildup from prior races, traction quality can change as a function of temperature. So this kind of just illustrates the way tire modeling works. I'm going to skip over this pretty quickly. But the tire actually deforms, as you see, as you put load into the tire. In this particular case, looking at what happens under acceleration. So let's talk about contact patches. So if you just think about, if you use paper like carbon paper, for example, or you use some sort of ink paper, you could put it under the tire and you'd see this sort of a pattern on it. How does the tire diameter affect the footprint? For a given width of tire, what would be different between a tire outside diameter of, say, 30 inches versus one at 15 inches? What would the...
I mean, the way I like to think about this would be to take it to the extreme. If you had an infinite diameter tire, you would have an infinitely large contact patch.
In fact, Russ, I think that's actually a great way to think about a lot of things, because I find that if I'm kind of struggling and trying to understand what happens, I will say, okay, so let's take it to the extreme. If we're like completely flat, or if it were stretched out to infinity, what would it look like? So that's right. And so what happens if you put more air pressure in the tire, other things being equal?
You would reduce the size of your contact patch?
That's right. And in fact, there's another example where if you said, well, okay, I could take it to 0, and Harry just showed me a picture with deformation, so it's not going to be completely flat, but yeah, if I stretch the tire to the point where it's got the maximum diameter, the contact patch itself is going to be smaller.
I would say that you potentially decrease your contact patch. If you're running
That's
too
right.
low, you could make it better.
That's right. That's exactly right. So what happens to load? Again, the important thing is that since all of the traction goes through the tires don't behave differently per se, because there's an independent suspension or a live axle. Certainly from things like camber angle, that is the deviation from perpendicular of the face of the tire with the pavement, that will change the contact patch. But as far as the tire is concerned, it doesn't know whether the load is changing because of the suspension design or not. It just reacts. So under acceleration, what happens? You transfer load from the front to the rear. Similarly, under braking, you transfer load from the rear to the front. And they're fairly straightforward calculations you can do based upon the rate of deceleration, the wheelbase of the vehicle, the height of the center of gravity, and the static weight distribution. So wherever the CG is, you can actually calculate what the braking force should be on the front and the back, and so you can design the brake system accordingly for that. But other things being equal, if what you were doing was a brake test and you had a car with, say, 50-50 weight distribution, if all you were trying to compete with in a stopping distance contest, would you in general want bigger front tires or smaller front tires? One way to think about it's the opposite of drag racing, right? Drag racing, the cars have evolved to use enormous rear tires and tiny front tires because all of the force has to be transmitted through the rear tires. And so I would guess, again, I've never actually done this, but I would guess, other things being equal, if the only test you were going to do was braking, you might want bigger front tires than on the rear. Anybody want to challenge that?
Depends on where your CG is.
Yep. Well, so what I said was a like 50-50 weight distribution. So are you speculating it also is a function of the height of the CG or just the?
Yeah, for sure. If the
for
CG is on the ground, then it won't move.
Then
But
it won't. That's
yeah,
right.
I agree with you for the most part.
Yep. So this kind of illustrates the load transfer characteristics of how you can determine braking force on the front. I think there's an interesting question that you might want to ponder is in terms of determining the optimal weight distribution for a Formula SAE car. If the event you want to optimize is acceleration, whether or not 50-50 weight distribution is the right answer. I strongly suspect it's a different answer if you're trying to optimize for skid pad, just constant speed cornering. And I think it'd be pretty clear if the acceleration event became an event where you had to get to, say, 60 miles per hour and then stop, and where the winner was the fastest car with the shortest distance to get from 0 to 60 and back to 0. I'm pretty sure you'd want a car with rear weight bias for that. So there's some interesting trade-offs, and I think trade-offs you make are very much a function of the kind of courses you want to compete on. So simple explanation of springs here. So the important point about people talk about what sort of spring rates are you running, you need to ask some additional questions in order to really get a handle on what's important, because in most suspension systems, the spring action is through a lever, and you can see in the diagram of the right here where there are a couple of lines for the upper control arm mount and the lower control arm mount with a spring attached to the lower control arm and to the body here. And so in order to determine what rate actually is at the wheel, you need to factor in the impact of this lever ratio. And in a Formula SAE car that uses push rods and rocker arms, there's another complexity in calculating that. It's all straightforward algebra, so it's not that hard to do, and the formulas are pretty straightforward. But when somebody says they're running, for example, a 350 pound per inch spring, in order to compare that to the different car, you need to understand the relative mounting positions and the motion ratios. So the difference is described as spring rate versus wheel rate, and there's actually a third way of talking about the stiffness of the suspension when you factor in the tires. And so the term ride rate usually means the actual rate at the contact patch, which is a function of the spring rate, the motion ratio, and the ride rate. So here's an example. this particular car has front springs about 500 pounds per inch. The motion ratio is 3.3, so the wheel rate translates to 151 pounds per inch. It uses a live axle with leaf springs at the rear. The rear springs are about 170 pounds per inch. The leaf springs are inset a little bit from the wheels, and so the motion ratio is pretty close to 1, not quite. But the wheel rates in this car are 154 pounds per inch. And this particular car is designed to have plus or minus 6 inches of ride travel, so considerably higher than a Formula SAE car. And so it goes to a maximum of 3 inches under compression. But the formulas apply to whatever kind of a vehicle you're using. So one of the things that people usually do in talking about spring rates is instead of talking about the pounds per inch, for example, they'll talk about the frequency of the spring system. And the reason that's done is because if you want to compare two different vehicles that are, say, two Formula SAE cars, depending upon the unsprung weight, that is everything that's not suspended by the springs. And so as the diagram shows, the components of the suspension and so forth that represent what's on the light side of the springs, if you will, if the body and so forth, and other assemblies of the heavy part of the vehicle. If the car has a much lighter tire wheel assembly, it can use a lighter weight spring. This is a common reason why independent suspensions are popular, because with so-called live axle or solid axle suspensions, where the differential is part of the unsprung weight, to get the same frequency, you have to use stiffer springs. And so for a given target frequency, the lower the unsprung mass, the lower the spring rate. Any questions about that? Okay, so a lot of engineers spend a bunch of time calculating spring rates, but in fact, there isn't a universal optimal spring rate that applies to any one particular type of car. And so what's important is what sort of tracks you're running on and what kinds of variations in surface, how rough the track is, for example. And there are a bunch of different factors that go into it. But basically, when you talk to people about determining the springs, they'll give you ranges of frequencies for particular cars. And I copied and pasted some from a website there at the bottom. You can see in general, the frequencies are a lot lower for passenger cars, and the higher the downforce, the higher the spring frequency here. And so if you ask, well, how are those determined? They'll say, well, they're determined empirically. And so what that really means is they tested the car and it was fastest with these springs and the driver said they control it. Or more often than not, people will copy whatever the leaders are doing. And so math can put you in the ballpark. And it is pretty interesting. If you look at, for example, passenger cars, there's 100% difference between a half a hertz and 1 hertz. And even the other ranges, you're talking about 30 to 40, 50% differences in ranges. So for given types of cars, these numbers can vary pretty widely. So let's talk about sort of what happens here. So this is an example of a wheel in a car going from left to right and running over some square blocks. And so the solid line in the middle plots the motion of the wheel relative to those blocks. And so if we then go to a stiffer spring rate, you can notice the difference here in that with a stiffer spring rate, it takes longer for the tire to regain traction. And then you can compare the two and you can kind of see them side by side. So again, this is a hypothetical, but it sort of illustrates the point. If you look at the stiffer spring, the loading on the tire is going to have higher variation. and it's going to spend more time for that sequence of blocks. It's going to spend more time where the loading on the tire is 0. And so if the loading on the tire is 0, how much tractive force can you put into it? Anybody? Ross, you know the answer to that.
0.
I kind of
Yeah,
stopped answering, but actually the mu, technically, like if it was 1 pound or whatever, the mu would actually be pretty good.
Mm-hmm.
You just can't get a lot of actual force.
Yep, indeed. So one of the other things that is not used in Formula SAE, some pictures here I actually pulled from a Subaru WRX forum showing what are called compression bumpers or jounce bumpers. And so I've left out dampers from this whole discussion. But dampers are a way of controlling the rate of change of suspension movement independent of the springs, and to dampen the cyclical action that happens if you didn't have dampers. But the dampers can also be another place to add a spring. And so production cars these days, this was really done by feel going back to the 1930s, where people would build test roads and then drive cars across them and sort of experiment with rubber, mostly rubber bushings. There were very sophisticated closed cell foam urethane these days in various shapes there that have various kinds of behaviors. But what the compression bumpers do, and they can also be used in extension, is they actually provide a way of adding a spring in parallel to the spring rate. So the impact is that once the jounce bumper is engaged, when the suspension compresses, you get increasing spring rate as a function of position. And so one of the things that's kind of interesting is about 10, maybe 15 years ago, NASCAR discovered these. And so now the top NASCAR teams actually have a full-time engineer, if not more than one, that's done all kinds of measurement and analysis, designs their own jounce bumpers, and they're as likely to change these as they are to change the springs when they want to change the spring rate. One of the things Joey Penniman did, I'd never looked at the underside of a Tesla Model 3, but according to Joey, the jounce bumpers engage with very little suspension travel. And there's actually a linkage. There's a guy named Craig Darien, who's a Formula SAE judge, who worked for Chip Ganassi on NASCAR and learned about these things. Most of the BMWs and Mercedes have very sophisticated jounce bumper systems. They pioneered it. Pretty much all of the car manufacturers now are doing a bunch of suspension tuning with these things. And I think often the difference between, for example, a sport model and a base model, the springs may in fact be the same, but they have tuned the compression bumpers. Craig was actually saying he 3D prints his own. So you can build a mold, you can get the material, and by changing the shape, you can also take ones off the shelf and cut them with a hacksaw or a bandsaw, and you can change the characteristics of these things. But what's interesting is, in poking around, people said, Formula SAE, nobody ever does anything like that. But I think there's pay dirt to be had in allowing. So what this would allow is, if you have variable rate suspension, you could actually run a softer spring, which would give you more even load distribution over small undulations in the track. But if you had a rough surface or bumps and so forth, or pitch under braking, it would be a way of increasing the spring rate, which wouldn't have so much negative effect of just increasing the rate all the time. I think it's
Harry, I've actually seen this on Graz's car in a video someone posted a couple weeks back, and then I started noticing it in a lot of European teams.
Oh, interesting.
Not bumpers, but helper springs. So they have 2 springs in series, and they have one that bottoms out, say maybe halfway through the compression travel, to give you a nonlinear spring rate. I'll send you a video.
Yeah. So I didn't talk about helper springs in this, but the idea of a helper spring is For those of you not familiar, they're not at pictures of these things. So typically very high downforce cars, where if you think about a car that generates enough downforce to equal the vehicle weight, what you'd like to have at low speeds when there's not much downforce is you'd like to have a certain spring rate, and then as the downforce, when you like effectively double the vertical load in the car, then you need much stiffer springs. And so you can imagine a linkage with typically a center spring. So they typically don't do them on each side of the vehicle, but you can arrange a mechanical linkage so that as the suspension compressed, the linkage would start to engage this third spring that would give you significantly higher rates. My personal opinion is there's a little bit of science and a learning curve to do it, but my personal opinion is in a Formula SAE car where you're basically talking about at most 50% of the weight of the car in additional aero load, I think the complexity of actually adding an assembly to do a third spring, while it's certainly more straightforward to calculate, but you can put these things in a spring checker and measure the rate. I actually think the simplicity of doing it entirely with jounce bumpers would be a win. But yeah, you can certainly do it with a third spring. Also, I was a little surprised. I was looking at a picture of a Pikes Peak racer which now they pretty much race strictly on pavement, but half of the Pikes Peak hill climb used to be dirt. And I was looking at pictures of this kind of quasi-dirt specialized vehicle with big wings, and in fact, it used a third helper spring front and rear, specifically because of the fact that they ran enough high speed where they wanted a different rate, but they needed low rate springs with a lot of travel to get over the bumps in the dirt. So let's talk about cornering. So this is some pictures from, I think, Long Beach, maybe Detroit. Interesting thing about that, what's the load on the inside tire in these two pictures? It really is 0. And so this is mostly cars hitting curbs. But these cars are stiff enough and the CG's high enough that the actual load on the inside tires is quite low. Top picture is actually one that Eric worked on, Formula San Jose student.
This actually happens, or used to happen anyway, in Formula SAE as well. OSU used to be able to lift their inside tires occasionally.
In fact, yeah, if you look at pictures of high rear weight bias cars, Porsches even, it's pretty common. My autocross Corvette, there are pictures of it with the inside front wheel almost off the ground. So it happens. In this case, I mean, look at the picture of the GT4 Camaro. I mean, its front and rear tires are off the ground there. So, different concept. We'll come back to that. Many of you are probably familiar with what's called a GG diagram or a traction circle. But what this is an XY plot where you plot braking and acceleration, longitudinal force in the up and down axis, and you plot left and right cornering forces on the horizontal line there. And so an important concept about a tire is even though it only rolls in one direction, most vehicles can generate about the same force under acceleration, excuse me, under cornering that they do under braking. And by that I mean, if you think about a high performance street car that can generate 1G in braking, and it probably also can generate about 1G in cornering. Now, Aero impacts that, and most passenger cars can't generate 1G in acceleration. So an important concept is that you can't both generate 1G under braking and 1G in cornering at the same time. And there's a relationship where the sum of the two components generally translates to whatever the maxim is in the direction. And so if you think about the picture on the right, illustrating that you can do some cornering and some braking with a result that the actual rate of acceleration is 1g, but it's during a transition from either braking into a corner from a straight line or accelerating out of a corner back onto a straightaway. So this concept has actually been around a long time. In fact, the guy who made the Valentine radar detector built a gadget in the 1980s called a G-analyst, which had a little 3-axis accelerometer, and you could put it in the car and actually use a display and get this. And so this was like the first time a really inexpensive way of doing it. These days, the Motex and so forth can output this, and the software generally allows you to plot it. So if you think about what a beginner on a racetrack does, they'll brake in a straight line, they'll go to the transition to the left or the right corner, and then they'll accelerate. And so if you think about the area on the outside of the curve, they're giving up a lot of time through these transitions. And so the other extreme is somebody assumes that they're full braking and they just assume that continuing with the full braking rate, leaving their foot on the brake pedal with the same force, and they start to turn, the car will veer off course because they're trying to get more than the tractive force that's possible through the tire as a result of that. Any questions about this part? You guys mostly familiar with this?
Yeah.
Some of you are, yeah. So in terms of how this translates to what the drivers actually do, because of this phenomena of trying to put power through typically the rear tires, what a fast driver will typically do is they will accelerate up to the point where they need to brake for a turn. In this case, the picture on the right here, on the left. At the point they start their turn in, they have transitioned from maximum bracing pressure to synchronizing, easing off the brake pressure as they tighten the radius in the corner. Make sense? In fact, one technique, this is sometimes called trail braking. That is, you trail off the brake pedal as you get to the corner. Now, the other thing that's shown is if you look at this and say, well, I don't understand, because if I wanted to just maximize the radius of this turn, I wouldn't do it this way. I would stay wider here, but then I would hit what's called the apex of the turn in the middle of the turn, and I would still be turning and going out to the outside here. But if you go back to that simple riddle I had about the motorcycle going halfway up the hill, one of the things about the way time is spent at a racetrack is the fastest drivers will look at a racetrack and they'll figure out where the longest straight is. They first arrive at a racetrack they haven't driven before. They'll figure out where the longest straight is, and they'll optimize the entrance speed to that straightaway. And by straightening out the trajectory here, what this allows the driver to do is to get on the power and be accelerating faster than if they drove this as a symmetric line. And the reason they can get on the accelerator faster is they've slowed down here and they've started to unwind the steering wheel. So if you look at the radius of this arc, it's quite a bit wider than what would happen if they simply picked the symmetric version of this turn. And so by straightening out the steering wheel, they can apply more power earlier, and so they are back then on the power faster, which means by the time they get to the end of that straightaway, they're actually going faster, and that's the difference. Anybody think of a downside of doing this?
Someone will come in on the inside.
That's exactly right. So NASCAR, they don't do this, because what happens in NASCAR, if they drove the ovals this way, everybody would come down the inside and take advantage of what I called that overlap accordion effect before. And they would prevent the driver from turning in. So there's a bunch of sort of high-speed chess that goes on when you put multiple cars in the track. But in general, this is fast. This also has one other advantage, because if you misjudge, you actually leave yourself more room to recover, because there's more room out here. If you misjudge, there's more room to recover and stay on the pavement as opposed to leaving the pavement. So it's generally considered safer. All right, so there are a bunch of forces at work. You guys all understand that. It's a function of the roll center height, the CG height, and so forth, and the various direction of forces here. Same picture as before. Let's talk about what's happening to the tire in a corner. So turns out that if you look at, let's say if you drove a car over a glass pane with a camera underneath it, you could look at what happens. The tire distorts, and one of the concepts that engineers talk about is what's called the slip angle, which is the difference between the angle of the tire and the trajectory of the vehicle. So if you look at what actually happens, is the lateral force builds up and it will actually distort the contact patch. And this is a pretty well understood and pretty well measured phenomena. So it's just a picture from one of the tire tests done at CalSpan where you can see the difference. Here's the case. The dotted line is the case of straighted head, and the one that somebody drew with a black magic marker to highlight the lines. You can see the tire contact patch is actually pretty distorted in this case of what's called 5 degrees of slip angle. So one of the things in terms of judging tire behavior that Ross has spent a lot of time looking at is curves like this, where you look at a plot of the lateral force generated as a function of the slip angle. And in this case, you can see it starts out quite linear, and then as the lateral force goes up, you hit a peak, and at this point, the car is drifting. And then once the slip angle increases, and those of you who watch drift contests either on television or in person where you see extremely high slip angles, there's a point at which the cornering force is maximum, and then as the slip angle increases, the cornering force actually falls off.
I'd be a little careful using drifting, depending on whether you're understeering or oversteering, but yeah.
Perfectly fair. Yep. Indeed, depending. It may simply be that the car wants to go straight as you increase steering input, for example. So those of you who've driven on ice or snow, you really know what this looks like, where you try to brake, and if you're trying to brake and turning, the car will just sort of go straight. I mean, the same phenomena happens in extremely low traction examples like what we're seeing here. The rates would be different. But I drew a hypothetical graph on this chart here, where if you have a tire plot where you get very rapid roll off as the slip angle increases, cars that have tires with this kind of characteristic generally are hard to drive. And race tires in general have steeper curves than passenger car does. Passenger car tires are driven to be pretty forgiving. So if somebody gets into an emergency skid, for example, they can easily recover. So again, the key thing is whether it's braking or acceleration, the less load that any one of the tires has at any point in time, the less force they can actually transmit. So there are kind of more plots you can look at that describe the same thing. So let's just touch on tire measurements. Here's a picture of a machine at CalSpan. And so what you're looking at is a belt that actually has sandpaper on it and a piece of machinery that can turn the tire. It can control the pressure. And this particular thing looks like, I guess it's a race tire. And they can then use this to turn the assembly so they can measure the effect of steering and cornering. And because tires are kind of a black box, this is the way that you can characterize a tire. So you put it through a whole bunch of tests and you generate a bunch of data, and then you generate plots from that. And those plots, the data from those things, can feed a model, what we call a behavioral model of the tire that can go into a car simulation. And so you get plots like this, and Ross and his vehicle dynamics team has spent a lot of time looking at these plots. The same kind of thing is that I showed you before with slip angles, a function of cornering force and so forth. So obvious way to continue contain body roll is through an anti-roll bar system, because it allows you to mostly decouple the roll rate from the spring rate, which is desirable. San Jose's Formula car uses them. Most race cars do. Depending on what you're trying to accomplish, if the tracks are smooth, you can use spring rates to do that with no anti-roll bars, which was Esther's recommendation to the electric team. So just as part of this, I dug out an old email I got from Terry Satchel, which in his experience, and back to my point about that there isn't in one right answer. Terry's comment, after having been GM engineer, worked for Penske, SAE, Formula SAE judge, and I know his son was a Formula SAE student when he was in college. His recommendation is, in general, 2 to 4 hertz was the range of spring rates that he thought in a Formula car. So let's talk about, and I'm running out of time here, so you guys are welcome to excuse yourself. If the car understeers, what do you need to do to the loads on the tires based on what you know now? Spring rates, anti-roll bar adjustments. What other things you could do? I've actually got a cheat sheet coming up here, but let's say the car understeers, so you have high load on the outside front tire in a corner. If the car understeers, what do you need to change?
Your steering angle.
Yeah, that's maybe one thing. So it could be drivers doing the wrong thing. But let's say the steering angle is optimal. If you
Your dynamic weight distribution.
So yeah, you could do that. Or so you could change the spring rates in the car, right? You could. So in general, if the car understeers, if you want less load transfer on the outside front, you can put softer springs in the front. Any disagreement with that? So you could put stiffer springs in the rear, softer springs in the front. You could change to a softer front anti-roll bar rate, or you could go stiffer in the rear.
Are you assuming steady state cornering, or?
Yeah, just steady state cornering. You could change alignment, which maybe your steering angle on the front tire is such that you have one slip angle here, and based upon your alignment
Tire size.
Let's say we can't do that. Let's say all we can do is adjust the car we have. We can't change what we have. But you're kind of warm. You could change tire pressures, right? Didn't we say that tire pressures, spring rate is a function of pressure? So we could change we could lower the spring rate of the front tires or raise the rear. That would be one thing we could change. So the point is there's several things there that not necessarily. So then there's another important concept, which is called corner weights, which is the idea that you sum the diagonals. And so in this case, the left front and the right rear, if the sum of that weight, have you ever sat in an uneven chair that rocks? You know, it's always the diagonal legs are what are too long. And so in a chair that rocks, there's one diagonal that has higher load on it than the other diagonal. So this notion of corner weighting is kind of the same. So you put the car on scales, you weigh the car, and you take the sum of in this case, the left front and the right rear, and you compare that with the right rear and the left front. So if you want the car so that it behaves the same in a left-hand corner and a right-hand corner, then you would want the weights to be the same. So let's take the case where, let's say the left front plus the right rear is higher because you've adjusted the spring pads, for example. So if that load is higher on that diagonal, what's it going to tend to do in a right-hand corner compared to a left-hand corner? If you have high weight on the left front, it's going to tend to understeer more in a right-hand turn and understeer less in a left-hand turn. That makes sense? Anybody not understand that? So this is actually so most cars in race series that are either autocross or on what are called circuits, road courses, where you have to go left and right corners. In most of that kind of racing, you start with a balance that's even. So you adjust the spring pads so that the so-called cross weights are identical. In circle track racing that only have to go one direction, they will actually change the cross weights, and in fact do it during a race, change the cross weights to change the understeer oversteer balance, because they only need to turn one direction. And so even if you're on a circuit, if you like Laguna Seca, so Laguna Seca, for example, is mostly left-hand turns. You might want to bias the car in a particular way using this. So even on a road course, people will adjust these kinds of things. And so you do it by adjusting the spring pads. You can also actually do it by adjusting the anti-roll bar linkage. All right, so here's sort of another summary picture here that all of the things to look at if you don't get the behavior you want. And I think I have a cheat sheet in here. Yeah, so here's a cheat sheet in order about what you want to change. So if the car understeers, you can either stiffen the rear ARB, soften the front, reduce the front tire pressure, increase the rear tire pressure, increase the front negative camber. And those are the A items. And then B, you can change the camber, change the spring rates, increase the front caster. And then the right side of this is preload. Okay, couple points on Aero. They're actually
before we go into Aero real quick, Harry,
sure.
I just want to point something out. So when we're talking about changing load transfer with springs, can you go back to you had a tire slip angle versus lat force, lat F for a given normal load? Yeah, I'll take this, sure. Oh. Any of these will work. So one of the reasons we're trying to change the load transfer is because the tires are non-linear, as we've explained before. So like at a given normal load, for different normal loads, you get different shaped graphs. And as you increase the normal load, the mu goes down. So the efficiency, so like if you got 100 pounds of normal load, you might be able, let's say the mu is 2, you get 200 pounds of lat force. But if you have 200 pounds of normal load, you don't get 400 pounds.
Yeah,
you
so
might get 350.
That's right. So it doesn't actually decrease. It's just that the rate of improvement declines. So
yeah,
you're diminishing returns. That's absolutely right.
Yeah. So when we talk about changing RBs and stuff, we can change the load transfer, which will change how much lat F you can get out of the tire based on, because you have, if we just look at the car, the back or the front two tires, you're shifting load from left to right if you're turning this way, right? So if we can transfer less load, then overall we can make more grip.
Yep. So, and so again, you're going to do a vehicle dynamics thing, so you'll probably get into that, if not in your presentation and questions. But there are a whole set of things around what's the right roll angle and what's the right roll rate, and as you know, those get to be complex discussions. If you think about running a slalom, depending upon your theoretical potential speed through the slalom, you might want the car to very quickly get to its maximum roll angle, so that as you transition the other way, you're not still rolling. Let's say if your first slalom gate is a left turn, and so the car is going to lean to the right in that situation, if you have an immediate right turn following that, you want to make the roll rate fast enough so that the transition the other direction is not while it's still rolling from the last corner. And so the transient behavior of those things, particularly if you're running courses that require slaloms, it gets to be a complicated kind of thing. And I think tuning and adjusting is the way you ultimately determine it's fastest. I guess
what I wanted to really get across was like, if that a heavier car will inherently be slower on the same tires because of the diminishing returns. Assuming all else is equal.
Yeah, exactly. Thank you. So there is a phenomena. The bias-ply Hoosiers are relatively, they're sort of less sensitive to cornering force as a function of vertical load than some other race tires, because, and the result is, I had this discussion with Terry a few years ago. The result is that the cars are relatively insensitive to changes in ARB stiffness. They're sort of less reactive than cars on other kinds of race tires. Now, he hasn't seen the plots probably of recent tires. It's been a while since he's been involved in Formula C, but so I don't know about the 16s. Is this something you observed in general? I remember looking at the GERS, but I wasn't focused on this point you're making.
I'd have to take a look. I can't tell you the sensitivity off the top of my head. It's going to still be there, but yeah, you may be right. It might be low or low-ish, or lower than Goodyears or Avons or whatever.
But good point. And I'm assuming you're going to get into that in your vehicle dynamics intro.
Yeah, but it's also going to come up when you start to talk about Aero as far as the normal load. That's why I wanted to cover it early.
So there actually is a machine in North Carolina where you can put a full-size car and drive it 200 miles an hour on a belt. But one important thing to notice about this picture, because you can see relatively high ground clearance between the front spoiler and the course, the belt. So compare that. Here's another picture in a wind tunnel where you have the splitter much closer to the ground, which is the way they run it. The picture sort of got smeared. This guy is actually a Canadian Formula SAE engineer who has kind of decided that NASCAR is not much of a family life for him, and so he just quit this past year. But he was a top crew chief. He was the youngest crew chief in NASCAR. His name's Cole Pern, and they won the 2017 NASCAR season championship. I remember an interview with him on Dinner with Racers. He said they spent 3 days in the wind tunnel testing different kinds of vinyl. So they've gotten very sophisticated in terms of aero. I think there's another picture here. Yeah, this one sort of illustrates it. If you look at where the front splitters are, so there's a part of the rule. These cars have to pass a minimum ride height they have to drive over a block every time they go out. So NASCAR checks the ride height of the car, but if you look them, this is probably going 170, 180 miles an hour. You look at them on the 1.5 mile speedways, and the front splitters are right in the ground. And so they have to have soft springs to allow the car to be high enough and get the splitter as close to the track to minimize how much air goes into the car from a downforce standpoint. And so this is the main reason they use jounce bumpers, is that they've gotten to the point where the spring rates are extremely stiff within a fairly narrow range because of the jounce bumpers. All right, just only a couple of points on Aero. We're almost done here. So if in general, if you look at the same kind of picture we had before with Aero, so the Aero is comprised of primarily a rear wing and a front wing. And the rear wings are in part usually bigger than the front wings because the front wing, at least unless there's a car in front of them on a track, the front wing is seeing relatively undisturbed air. By the time the air gets to the rear wing, there are all kinds of things going on. And so a fair amount of work is done with respect to side pods and so forth to direct the air over the rear wing. But between the downforce on the rear wing and the downforce on the front, you can calculate and measure, in fact, a point. If you've got a way of measuring downforce with either suspension travel or load cells, you can calculate what's called the center of pressure, which is the effective midpoint between the weighted downforce in the rear and the weighted downforce in the front. And so in general, if you're in a situation where the center of pressure is forward of the CG of the car, then you can imagine at low speed compared to high speed, if the center of pressure is forward, relatively speaking, there's going to be more vertical load on the front wheels than there is on the rear wheels. And so the result of this being forward of the center of gravity is that understeer is going to be lower, or in other words, increasing toward oversteer at high speeds with this kind of relationship. Most race cars are designed so that the center of pressure is either at the center of gravity or rearward of the center of gravity. And the reason being is at low speed, you may actually want oversteer, particularly on like a Formula SAE car where you have very tight low speed turns, where if you can use mechanical oversteer to help turn the car in a corner at low speed. And at low speed, things aren't happening fast enough that you can't correct by countersteering, for example, or taking action with the throttle position to correct from an oversteer situation. While at high speed, even though Formula SAE courses have a lot of runoff, it still is pretty uncomfortable to deal with a car that changes from understeer to oversteer as speeds go up. If oversteer is predictable, it can be pretty controllable, but you have a situation where if you're at high speed and the car tends to oversteer, in general, what you need to do is slow down. And so whether you simply reduce throttle or apply the brakes, then you get a mechanical load transfer effect where you transfer load to the front wheels, which further unweights the rear of the car, which tends to increase the tendency to oversteer. Does that make sense? So in general, what people want is, if they want oversteer, they want it typically at low speed. At high speed, you want a small amount of understeer typically. Because if you have understeer at high speed, you can, by reducing throttle, you get this load transfer effect, transfer load to the front, which will naturally reduce the understeer intensity. So it can make it easier to drive. All right, so final exam question. You have a Miata. You're in second place at the SCCA Autocross Championships. You're only 0.4 of a second behind. You have one more run and your car understeers. And unfortunately, while you're out in your last run, somebody stole all of your tools. So the only thing you have left is an old toothbrush. How can you use the toothbrush to reduce your car's understeer?
You can dump some tire pressure or clean off the tires really carefully with a toothbrush.
Now there's a good answer. Yeah, so I was thinking, I was figuring exactly the formula is that if you can't work the tire valve with your finger, you could use the toothbrush handle to let some air out of the front tires. So that's the answer. Any questions? Very good. I'll make the slides available. Thanks for your time.
I have one more comment, Harry, if you wouldn't mind going back to the GG plot real quick.
I skipped over this one. Is that okay, or do you want me to go back?
Actually, no, this one's perfect. So in this one is 180 degrees or mirrored from what Harry had.
Yeah, in fact, I should change that because this is backward. In this case, acceleration is this direction, braking is this direction, and it's flat because unless it's a really high-powered car, you're not going to be able to accelerate as fast as you can brake or corner.
That's exactly what I was going to get at.
Yeah.
One thing that's so I guess if you want to add another fun question, what's the optimal power horsepower that a car can produce? It's enough to brake traction on the rear tires at all times. Not that would be particularly easy to drive, but it would allow you to stay out here on the GG plot at all times. So basically infinite horsepower.
Yeah. So do you know the Mark Donohue quote?
Yeah, that's where I got it from.
Yeah. So Mark Donohue was unfortunately killed. He was hit by a tire in a practice session for a Formula One race. And he ended up not realizing that he had serious brain damage and it bled to death. But Mark was an engineer by training, drove for Roger Penske in the 1970s, 1980s. And they ended up in a project with Porsche that at first Porsche said to Penske and Mark Donohue, you're the driver, we're the engineers. You do what we say. And so they started making suggestions on how to tune this car. And the car in particular I'm talking about is a 91710, which you can see pictures of. So the 91710 was a derivation, a roadster version of the Porsche Coupe, the 917 that was used in the Paul Newman, I'm sorry, not the Paul Newman, what's his name? Blanking on his name.
Steve McQueen.
Steve McQueen, the actor who did the movie about the Le Mans 24. And so those Porsches were modified, turned into roadsters, and they raced in the SCCA Can-Am series. And so these things, in fact, I pull up a picture.
The last of the really high power air-cooled engines.
Yeah, so this one in particular was the final one they did. Right. So they weren't very clean aerodynamically, but these were they built several versions of them with various numbers of cylinders. But this was a flat multi-cylinder Porsche engine with dual turbochargers, and the red and white one was raced in '72, and this one was Sunoco. There's actually one that was built from parts like it at the vintage races. The original one of these is in the Porsche factory, but this thing routinely raced with 1,300 horsepower. And so Mark Donohue was quoted after driving this car as saying, he said, there's enough power when you can spin the tires from the beginning of the longest straight until you have to put the brakes on. He said, that's when you have enough horsepower. But they actually built one that was 12 cylinders. When they raced this was a 8-cylinder with dual turbocharged. They built one prototype and several engines that were 12 cylinders, no turbochargers. And there was one actually at the Rennsport reunion at Laguna Seca a few years ago. They brought it out of the museum and they showed it. And so they said that if they ended up not using it, but they said if the V8 turbo wasn't powerful enough, they were going to turbocharge this 12-cylinder, which they assumed they could get somewhere between 2,000 and 2,500 horsepower. But the net result of this car so dominated the competition that the Can-Am series basically ended. Nobody else wanted to try to compete with them. They used beryllium brake rotors. It was a pretty amazing piece of engineering. Anyway, yeah, it's exactly right. Is that in terms of the GG forces, you're going to see this sort of a plot with a flattened top typically, because you can't generate the kind of forces, acceleration in most cars that you can braking, and you probably can't with two-wheel drive fully put it to the ground with a car that has to go around corners as well. So it takes four-wheel drive probably. But really high performance street cars, my autocross Corvette would generate 0.76 Gs in low gear. High performance McLarens, things like that these days are about a G. I think with a Tesla S, you can probably generate close to a G for a while in acceleration. I think 1 G is somewhere around 0 to 60 in 3 seconds, something like that. So any of those cars can get to 60 in the vicinity of 3 seconds, can generate a G in acceleration, including an FSAE car, I imagine. Anything else? Thanks for your time, guys.
I wanted to say thank you, Harry. This has been really awesome. Very
You're welcome.
informative. Thank you.
Thanks, Harry.
Thanks,
You're
Harry.
welcome.
For the presentation, Harry.
Thank you.
You're welcome. I'll send the slides out. Enjoy your weekend.